Hello. In this CoCoA lecture, we are going to talk about the division algorithm referring to Grosvenor basis computation. So in this first part, we want to get ready with the idea, with the concept of multivariate division. And for doing that, we first recall some nice property of the univariate division. That is what we would like to mimic in the multivariate case. So one nice property that we have in the univariate case is that QQ of X is a Euclidean domain. That means it is a PID, principal ideal domain. So every ideal is generated by just one polynomial. That means that when we want to divide, we divide by one polynomial, which is the generator of the ideal. And the very nice property we want to reproduce in the multivariate case is that when we have an ideal, a polynomial f is in this ideal, if and only if the remainder of the division of f by the generator of the ideal is 0. So we have a nice criterion to say when a polynomial is an ideal. Now, when working with multivariate polynomials, we already know that this is not a PID, so the operation we want to do is to divide by many polynomials, which are the generators of the ideal. And so we start investigating this concept by doing an example by hand, because it's, after all, is doing things by hand that makes you understand the technique. So we have a polynomial ring, Q of X, Y, Z, and we have a polynomial, I'm not reading it, and we have two generators of an ideal, G1 and G2, and we want to invent a division between F and the list of G1 and G2. So that means we want to compute two quotients, Q1 and Q2, and the remainder R, so that F is the product of Q1 and G1, Q2 and G2, the sum of the products, Q1 by G1, Q2 by G2, and a remainder, where ideally no term in the remainder R is divisible by any of the leading power product of G1 and G2. So we shall do an easier thing. We now concentrate just on the leading power product, and we do a head reduction instead of the full reduction of all the terms in the polynomial f. So we start with this simple, easy strategy. First, we check if the leading power product, the leading monomial of f, is divisible by the leading monomial of G1, the normal division that we know. Then, if not, we look at the leading monomial of G2, and we repeat this process on the remainder until neither G1 nor G2 divides the leading term of the remainder. So let's do it so we can understand it better. So the first remainder is given by f minus x times y times G1. Indeed, the leading power product of G1 is x and y, which divides the leading power product of f, and the division gives x times y. So I subtract from f, x, y, G1, and I get the remainder, which has this new leading monomial. Then I check if G1 again divides this leading monomial, and it does because x times y divides a square y. So I multiply G1 by x and subtract it from R1, and I get the R2, the second remainder. And the second remainder is now x y squared plus blah, 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 blah. Now, again, G1 divides this leading monomial. And so I multiply G1 by y this time. And I get this third remainder, whose leading monomial is x squared. And then this is not divisible by G1, because G1 has leading monomial xy, but is divisible by G2 because its leading monomial is x squared. So I just subtract G2, and I get this new polynomial. Again, this is divisible by G1, so I compute the last remainder, and we have that this is a polynomial whose leading power product is not divisible by neither G1 nor G2. Indeed, in this case, even the monomials in the tail are not divisible by the leading power product of G1 and G2, but this is something we will investigate in detail later on. So we have found Q1 and Q2 and the remainder, and we have that indeed F is this Q1 times G1, Q2 times G2 plus the remainder. Now we want to compute more things of this kind, and indeed in CoCoA we have functions doing this for us. And the functions are the division algorithm, divAlg, which does exactly what I told you before. So we get the quotients, Q1 and Q2, and the remainder. And we have just the function giving us the remainder when we do not care really about the quotients. Usually, we in Grosvenor basis computations, we don't really care about the quotients, we care about the remainder. So that's why we have the normal remainder as a function in CoCoA-5. Recall that this is a Q of x, y, z is not a Euclidean domain, not even a PID. So there is really no hope for uniqueness. If we had a unique remainder, it would be a lot easier. So we divide by G2 and G1. What does it mean? That we look at the leading power product of G2 first, and then if G2 doesn't divide, we look at G1. Then we get different results. Of course, we get different quotients, but we also get a different remainder. Look, this is the remainder after dividing by Q1 and Q2. Q2 and Q1, and this was the original remainder dividing by Q1 and Q2. So again, we can call directly the normal remainder function, and this really highlights that we can have different situations. Now we want to learn how to use CoCoA. We want to investigate more in Grosvenor basis. We want to make variants of this algorithm. So we are now going to write our own version of the normal remainder. So we can experiment, we can modify it, we can investigate, we can get inspiration for more general applications. So the first step that we need to do this is to write a function that gives me the candidate reducer in a list of polynomials. So we said, what did we do before? We checked if the leading power product of G1 divided the leading power product of our polynomial. If not, we look at the second. If not, we go on in the list. So we have a list of reducer. We call it L, a good name, L for a list. And we want to return the smallest index such that Gj divides the leading power product of Gj divides the leading power product of Rf. F should be F. Then we will see that we use the trick if we do not find a suitable J. So let's start from the naive version. The naive version is this. That means that I run through the indices from 1 to the length of the list L. If LPP of F is divisible by LPP of Lj, then return J. That means the first index that we find is returned by this function. When we hit return, the function exits immediately. So if the first polynomial has the leading power product dividing the leading power product of F, then just one cycle in this loop is done. So we test it. On the example before. We recall that F, we write it, F. The leading power product is a squared y squared. So this should return 1. That is what we did by hand before. And it does. I test on some more examples just to make sure that my function does what I want. So in this list, the first polynomial dividing the LPP of F is the second one with a squared, and indeed we get 2. And then we need to start thinking of the extreme cases. So what happens if I call my function with a polynomial 0? This is an extreme case, but that might come out of an exercise. So I get an error, which is not really easy to read. So it says that something went wrong in my file. Is exactly in this line, and I have a problem computing if is divisible at LPP of F because it says found an integer instead of a ring element. Even if it were a 0 of the ring, it would not be able to compute the leading power product of the 0 polynomial is not defined. Now I show you another error. Again, here I have an error saying that a function must explicitly return a value. So if in my function, like in this case, I have a return, it must return something for any input I give. So in this situation, I have nothing in the list. The list contains only z cubed. I have nothing in this list that divides the LPP of F, which is s squared y squared. So as a human, saying there is nothing is okay, but as a program is not. I must return something. I cannot return nothing. So what can we do? There's a common practice in this case that when there is a list of possibilities and a nothing to return, then we return something which is obviously wrong. For example, if there is no element in the list dividing F, we return 0, which is an impossible index because indices in CoCoA 5 start from 1. So like we normal human people do, thinking of the first element of a list, the second, and so on. Whereas in C++, indices start from 0. But now we are talking to human. So saying that the 0th element is the element dividing is obviously a wrong answer, which tells me there is nothing good in that list. Indeed, we could even throw a meaningful error saying there is no, an error saying there is nothing dividing my polynomial f. That's another possibility. In this case, we prefer not to return an error, and we will talk about what happens when we return an error in a following lecture. So if we return 0 when the polynomial is 0 or there is no possible answer, then we can detect it. We can detect it. If the answer of this function was 0, then we can do other things and deal with this problem. So here is how we modify our function. So first of all, we check, because if f is 0, then we return 0. There is nothing to do. F is just as small as it can get. And if we exit out of this for loop without getting out of the function with a return, it means that there was nothing dividing my polynomial f, and so we return 0. So in both cases, I don't need really to distinguish them. We will see how we use it later on. In both cases, we return 0, as to say that there is nothing to divide. So now we read this new version with the source region. And of course, in the normal case, the usual inputs, it works fine. If it's 0, I have 0. If there is no possible reducer, I get 0. In the next lecture, part of this lecture, we will see how we use this function to implement the division algorithm. See you later.